ENAV and the challenge of SESAR validation. The evolution of the European scenario has led to embrace a new perspective, based on the principle that the realization of a true single European sky will be feasible only through the endorsement of a European vision and approach to the air traffic management system modernization. SESAR, the Single European Sky ATM Research, is the R&D program to develop the future ATM system in Europe capable of ensuring the safety and fluidity of air transport over the next 30 years. It has been launched as an integrated element of the Single European Sky legislation, and it represents its technological pillar. It aims at developing a modernized and high-performance air traffic management infrastructure, which will enable the cost-efficient, safe, and environmentally friendly development of air transport. The SESAR program is a joint initiative between the European Commission, Eurocontrol, and the entire aeronautical sector. 110 companies participate with their experts, air navigation service providers, airspace users, airports, manufacturing industry, and military, all working together to make the program a success. ENAV, the company that provides air navigation services in Italy, is one of them.
ENAV is robustly involved throughout the whole SESAR program and is leader of Working Package 3, the working package in charge of validation. ENAV is fully committed to perform validation campaigns on the most promising operational improvements in line with the business priorities set by the Tiger team, taking also into account the expectations of both external and internal stakeholders.
One of the key principles in SESAR is to validate mature concepts, procedures, and technologies in an operational environment to assess the real-world benefits.
ENAV SESAR experts work in strict coordination with the operations to adapt the exercises so to accommodate SESAR validation expectations for the future concept of operations, while producing quick wins to improve today operational methods, as well as providing guidelines for the ATM systems which are being deployed today.
A day at Roma Experimental Center, validating SESAR TMA concepts.
Green and ready to start simulation.
In Europe, a centralized traffic flow management function ensures that the traffic demand for any given airspace sector does not exceed the local capacity. This is done, when required, by regulating the departures at originating airports, thus delaying aircraft on the ground, typically at the parking bay with engines off or idle, which is less costly than holding them once they are airborne. One of the outstanding goals of SESAR is to develop operational concepts and technologies which optimize ATC arrival capacity while minimizing flight inefficiency resulting from vectoring and holding activities. Once aircraft enter the area of responsibility, controllers predict future aircraft positions using the agreed flight plans, current positions, and speed vectors. They then act tactically by asking the crew to change the horizontal or vertical path, or to modify the aircraft speed, whenever this is compatible with the aircraft performances and speed envelope. During the exercise, ENAV controllers sequence the incoming traffic to optimize the flow, guaranteeing both high and constant landing rate while keeping the aircraft correctly separated from each other. The exercise is complicated by the different approach and landing speed, which is required by different aircraft types, and the applicable separation minima due to wake vortex, wind, and visibility conditions. Tactical rerouting, speed adjustments, or changes in flight levels have a negative impact on the overall performance of the system. Aircraft may travel longer and have a rather unpredictable time at arrival, which may furthermore compromise the planning of the surface operations and turnaround events. To improve the efficiency of air traffic management in complex terminal areas, an arrival manager tool, also known as AMAN, is used to assist controllers in correctly sequencing inbound traffic so as to feed the runway at the optimum rate. By extending the horizon or look ahead of an AMAN tool into en route sectors, aircraft can be requested to absorb delays or gain time by minimum speed variations with minimal impact on their 3D agreed path. This allows ENAV controllers involved in the exercise to build the arrival sequence of flights much earlier than is possible today. The goal is a better management of throughput, ensuring that delay is managed in the most fuel-efficient and environmentally acceptable manner. At airports where extended arrival management is deployed, the final flight path to the runway becomes much more predictable and can in fact be flown on fixed routes as opposed to today's operations, where controllers apply extensive radar vectoring at medium to low altitudes to achieve the required sequence and spacing. Equipped aircraft can also be requested to commit to a precise required time of arrival, or RTA, at a waypoint along its route. In this way, the flight crew can use their avionics to achieve the most efficient speed profile whilst respecting a commitment to precisely arrive at the waypoint on which the RTA was applied. Aircraft delivered to customers today are equipped with systems that can display the position of surrounding traffic thanks to ADS-B. These displays are known as Cockpit Display of Traffic Information, or CDTI. Provided with the identity of the aircraft immediately in front and the required spacing interval, the flight crew of aircraft in trail can use avionics to continuously calculate the optimum speed to be flown so that a required spacing in time is efficiently achieved and then maintained until final approach. This technique is known as airborne spacing, and it was investigated in depth in a number of validation exercises conducted at ENAV Experimental Center.
What we can see here is the final approach section in Rome Fiumicino. We are currently having 6 airplanes linked and performing ASPA approach. Basically, the minimum spacing applied is 90 seconds. Occasionally, there might be a larger spacing according to the tactical conditions in which the approach is being carried out.
Airborne spacing reduces controller task load per flight, accompanied by a minimal increase in flight crew workload thanks to avionics automation. This is accompanied by an increase in flight crew situational awareness, which is also considered a safety benefit.
Expected benefits coming up from ASPA utilization is the runway throughput to be optimized in terms of spacing accuracy between successive landing aircraft.
Extended AMAN, required time of arrival, and airborne spacing techniques can all be applied to traffic approaching a complex TMA, resulting in a balanced and predictable inbound sequence of landing traffic matching airport capabilities and ground logistics for efficient turnaround. The result of ENAV validation experiments has shown that pilots' and controllers' workload is minimized, as well as distance flown, fuel consumed, and finally, environmental impact. Validation requires high-end technologies and a lot of time and effort to ensure the expected results.
ENAV fully supported the adoptions by SESAR of the industry-based platform approach for validation. Though it increases complexities and reduces flexibility in accommodating real-time simulation, it assures a straightforward portability of the results into the real operational world. The expectation is to shorten the R&D cycle significantly to rapidly provide ATM with the level of innovation needed to cope with the future challenges.